Hello, everyone. So my name is Filip. Pedro was supposed to be in person here. Unfortunately, he couldn't make it. And a lot of the work that we're going to present, he actually did a bunch of it, the bulk of it. So we've decided to make this a hybrid presentation where Pedro's part is pre-recorded. We're going to play that in the first part, and then I'll do the second part like live in person. Before we get started, I'll just briefly introduce both of us. So my name is Filip, as I said. I am a production engineer at Shopify, where I work with Pedro on the metrics team, and we handle everything from kind of metric collection to ingestion, alerting, dashboarding, all of that stuff. Also, I'm currently helping maintain the Thanos project, and in the past, I've also been involved in Cube State Metrics and Prometheus Operator. Pedro, he's obviously not here. He is originally from Brazil, and he's currently mostly involved in the Keda project. So what we'll talk about today is very closely related to what you heard about OTel and push-based and Delta yesterday. We'll briefly talk about how applications are instrumented at Shopify, and spoiler alert, we still use statsd. We'll briefly explain the statsd protocol. Maybe just a quick show of hands. How many people here have heard of or use statsd? Wow, okay. So yeah, this will be very relevant for you. And finally, we'll kind of explain how we've I would say, successfully managed to merge these two worlds of push-based deltas with pull-based absolute value scrapes. So at this point, I think I'm going to kind of hand it off to virtual Pedro to do the first part.
Hello everyone, I hope you're having an amazing PromCon so far. Before I get started and talk about the solution we adopted for custom metrics at Shopify, it's important to understand how we work and how our developers interact with infrastructure at the company. At Shopify, we have a long history with Ruby and Rails. We also have one of the biggest Ruby apps written and deployed in production, which is our monolith with over millions of lines of code. We also use Ruby as default for all of our product development, and apart from that, we use Golang and Rust for systems as system programming languages. We also have an in-house application platform where developers, they don't need to think about Kubernetes resources, but rather they think about what their application needs to work properly, like one web server, one job worker, and the application platform will take care of deploying the underlying Kubernetes resources. The journey towards the solution we are presenting today started for my team when we began a migration from a vendor solution towards a Prometheus-based observability stack. At that moment, the applications were using statsd as default for metrics instrumentation, and we even started looking into migrating those apps to use Prometheus-based instrumentation, but we had this huge code base already instrumented with statsd, and we also saw that Ruby lacked a good implementation of Prometheus native instrumentation. We also had some short-lived workloads, which poses a challenge for the pull-based approach that Prometheus uses, such as machine learning jobs and even short-lived job workers. So we decided to use the statsd exporter. Using the statsd exporter, you can convert metrics in the statsd format into a Prometheus native representation. We also are deploying the statsd exporter outside of the application, so developers don't need to think about this extra piece of infrastructure touching their applications. And we allow users to configure the metrics through a web UI, and then we would sync the configuration from cloud storage to the statsd exporter instances using a sidecar. We also were early adopters of the native histograms, and we managed to actually retire all this web UI for configuring metrics and just using native histograms for all of our metrics. Before we talk about the first iteration of our solution, let's talk about the statsd protocol and statsd. statsd was initially developed as a daemon to summarize metrics from applications. it has some design principles, like being simple. This meant a simple protocol and a simple way to instrument your applications, and also had in mind to have a small footprint because it didn't have any state on the client side and was using UDP as the protocol, so the applications could not be crashed from metrics instrumentation. The text-based protocol from StatC works like this. You have the metric name, a value, and a character representing the metric type. So for a counter, you could have a metric called metric name with a value of 3, and then a C representing the metric type of a counter. For histograms or timings, as they are called in StatC, you could have a metric called some latency, then a float value representing milliseconds, and then the metric type, which is H, in this case representing histogram, or you can also have MS representing a time. And you could also have a gauge, for example, using to measure temperature with a value of 40 and a G for gauge. So our first setup looked like this. We had the application sending metrics via UDP using the StatC protocol to a daemon set running in our clusters. This daemon set was the vendor agent from our vendor solution, and it would forward all the metrics to an envoy proxy running as a sidecar. This envoy proxy took care of load balancing all these UDP requests against a set of Prometheus StatC exporters. After a while operating the solution, we had some problems with it. Mainly, some of applications were sending metrics at such a high rate that the StatC exporters could not keep up. Also, we had high series churn in the StatC exporters because the envoy proxy was doing a great job of load balancing the requests, but it didn't have an idea about which series it was sending to every exporter. So in the worst case scenario, you could have one single series living in not every instance of the StatC exporter, causing huge cardinality and also causing high series churn. So our main takeaway from this first iteration was that we needed some tool to protect the StatC exporters from getting these high data rates and also to ping series to specific exporter instances. This way, the exporters would only keep in memory some subset of the series that were created on that cluster. We also had problems with the StatC exporter itself. As I mentioned, the throughput was not as expected, and we also knew that we were using it outside of its use case, where it's usually deployed as a sidecar to the applications you are observing. We had some problems with counter and histogram resets due to the TTL we were using to deal with churn of metrics in the exporters, and this will be probably solved by the created timestamp being introduced in Prometheus. We also had high memory usage due to the StatC parsing algorithm, which was creating a lot of strings in memory during parsing. To solve some of those problems, we decided to fork the StatC exporter. First, we introduced the 0 samples on the first scrape of counters and histograms, which looked like this. You had a counter at some point in time. You would include a synthetic sample on the first scrapes of the counter to make Prometheus calculate the rates correctly. We also improved the StatC parsing algorithm to use less memory, and we introduced parallel parsing of StatC samples using coroutines and buffer channels, among some other contributions that we managed to submit upstream and got accepted. Now that I talked more about the StatC exporter and how we work at Shopify, I'll leave to Filip to talk about the StatC load balancer and how it plays a crucial role in our solution. Thank you very much.
Cool. All right, so with kind of that context, now that we have that context, we wanted to briefly explain why we have this component called a load balancer for StatC packets, and why it plays such a crucial role to allow us to handle the amount of data that we have. So as Pedro mentioned briefly, the canonical way or the typical way you would run the StatsD exporter is to deploy it as a sidecar to an application that emits StatsD metrics or metrics in the StatsD format. Then each application would talk to this local sidecar and will set packets to this local sidecar. The sidecar converts that to the Prometheus exposition format, and Prometheus can then scrape the sidecar. Now, at the scale that we run, there are several problems with this approach. First is, if we imagine that we have this kind of very simple small metric called checkout duration seconds, let's just say that it has cardinality of 1, so it has no tags, no labels. When each application kind of emits this metric to the exporter, that metric is going to be created in each exporter. And when Prometheus scrapes exporters, it's going to attach what we call target labels. And now what we've done is we've gone from cardinality of 1 to cardinality of 3. So we get this kind of inflation of cardinality by attaching target labels. Now you can't just drop these target labels. They're required to do aggregations when you're kind of pulling metrics. So for us, because of this kind of property and behavior, this was creating a lot of, like, with hundreds or thousands of instances, this was creating a lot of, this was very cost ineffective to run this way. The other problem is we don't actually own all applications, so every application would then have to create a hard dependency on this sidecar that we kind of are on call for, and then we end up being on call for every application out there. It's hard to roll forward, it's hard to roll back. Things just become very, very messy. And then the next iteration of that, you can still run the exporter as a daemon set. And this is something you can typically do if you run the OTL collector, for example. It's common to run the OTL collector as a daemon and then interact, like every application on the node will interact with it. The cardinality increase that you get is not as high. Now the scrape target is actually the node, but it's still higher than the original cardinality that the application metric has. The other downside is you get very uneven resource distribution. You get a lot of hotspotting. Some nodes become very resource intensive, and you need to kind of, every node basically, or every exporter on a node becomes a snowflake. You need to manage resources manually. And you also tend to kind of reduce the size of your clusters because you have to allocate a certain amount of memory to each node and to each exporter, and each exporter runs on a node. So your cluster size kind of shrinks. And so this is where we've kind of decided to go with somewhat of a crazy hybrid approach of introducing this thing that we call the packet load balancer or a StatsD load balancer, which is still a daemon set, but it's much more lightweight. It's basically a domain-specific proxy for StatsD packets. It uses DNS discovery to discover kind of downstream exporters, and it uses a method called consistent hashing to pin individual series to an exporter. This allows us to also autoscale these exporters, so we don't have coupling between an exporter and an instance or an exporter and a node, so they are fully decoupled for the lifecycle of the application. So now when all applications or all instances, for example, emit this one metric that has one time series, that time series will end up getting pinned only on one exporter. And when Prometheus scrapes the exporter, it's still going to, we end up paying this cost of cardinality of one time series. So now that we've kind of built this pipeline, or maybe to just talk about the drawbacks. So the drawbacks here are that we don't get this up metric, for example, that you would get when you scrape a target directly. But for us, these application metrics, we consider them to be business metrics or domain-specific metrics. So we don't really care about, we never want to get a breakdown of how many checkouts we have per application instance. That's not something that adds value to us. So kind of losing these up metric or losing target labels is a perfectly acceptable solution. To illustrate why this is so effective at our scale, this chart shows the amount of, or the ratio of nodes to exporters broken down per Kubernetes cluster. And we see that in some clusters, we have as many as 150 times more nodes than we have exporters. So we're able to handle all of this metric load with far fewer exporters, and we don't have to pay very high cost for cardinality. So now that we have this kind of pipeline in place, we were also able to add various checks in the pipeline that are that allow us to drop metrics, so we can drop them at the load balancer level. We can enforce certain label limits. For example, we can detect things like whether a shop ID was leaked or whether a customer ID was leaked in the label name. We've also had things like Ruby objects getting shoved in the label values, so we can also drop those in a much more efficient way. But the biggest benefit that we get from this kind of pipeline is that we can actually safely drop labels, which is not something that we can do with relabel configs. So if we take this very simple example again, where we have a checkout metric, it has 2 time series, gets emitted from one instance, and we have this user ID label here, which we've, let's say, determined is very, very high cardinality, as it usually is. So with a push-based, delta-based model, we can simply drop this label, and from the load balancer is going to send checkouts 3 and checkouts 1 to the exporter, and because these are deltas, the exporter is going to aggregate them. It knows that this is a counter metric, so it's going to sum them up. If we did this with Prometheus, for example, if we dropped the label with the Prometheus relabel config, when Prometheus scrapes the target, it will see a time series checkouts with a value of 3. It's going to ingest that. And then the next series is going to have the same label set as the previous series. So the second series will actually get ignored. It will get dropped from the scrape as an out-of-order sample. So if we drop labels with Prometheus, we can actually lose data if we're not careful. Yeah. Now, there are definitely downsides to kind of having, pushing deltas. We see a lot of, for example, hot loops. This is not actual code, but let's say it's based on a real story. If we have a hot loop like this, where we kind of try to get something from Redis, and then if the key exists, we call this stats the increment method. This actually doesn't increment the value in memory. If you're not careful, this will actually push a packet. So your client has to be kind of sophisticated to do local aggregations first before it emits values. But then in a language like Ruby, where we cannot aggregate across requests, the more popular the service gets, the higher amount of traffic it's going to generate for metrics. And so this is why we've decided to kind of solve this problem at the load balancer again. So we would, on a very small interval, like a few seconds, we will batch packets together. We will do the local aggregation. So in this case, we know this is a counter. We know these are deltas. We'll sum them up, and then we'll forward that to the exporter. So probably we get some out-of-order aggregations here. It's probably not as precise as when you scrape with Prometheus, but again, for the cost-benefit ratio for us is fine. And yeah, this also kind of chart tries to show why it's kind of so effective to do this even at very short intervals. This chart shows the amount of incoming versus outgoing packets. And we see that we're able to kind of reduce the bandwidth that we use by about 95% just by having very short-lived, a couple of second buffers. All right, and then that's kind of the overview of the solution, what we're looking to do Next, and what we're currently working on is having more proactive label dropping. So we want to have more automated detections for high cardinality, and we want to be able to drop labels before we ingest that cardinality. So this chart here on the right side shows a case where we were taking, developers were adding kind of unsanitized user input from a form into a label value. So during a flash sale, the amount of values in this label just exploded, so we ended up ingesting 200 million time series just from one metric. Obviously, this makes the metric completely unusable. You can't query it, you cannot do anything with it, so we might as well just drop it if we detect something like this. Serverless environments can also be very challenging to pull metrics from, so we think this might be something that we're looking already into approaches like this for serverless, and we're also kind of eager to see what the OTLP support is going to bring to Prometheus and whether some of this can be replaced or maybe more tightly integrated. And that's it. That's all I had. Thank you very much.
All right. Any questions? Yeah, you should. We messed up. Just go for it. Any questions? Oh, yeah, okay. I'm going to go with this one for now.
You mentioned that you were mainly looking at business type metrics where the instance doesn't matter. Do you have any need or situation where you do want to be able to locate a pod that's failing, a node that's failing, things of that nature?
Yes, definitely. But we think that we get enough information from kube state metrics, cAdvisor, so from infrastructure metrics that actually monitor pods and nodes. So what we don't want is to have target labels on each business metric, but rather have one metric maybe that has these target labels attached.
Any other question? Okay, so I have a question, if I can. So you mentioned the proactive kind of like stopping of this tsunami, and you mentioned the dropping labels and various kind of like enforcers verifications. How the source of this metric is notified that they're making problems and that their valuable information is not actually monitored for some time? Like, is it a problem? How you kind of like notify these people? How you, like, is it like you have to manually do that? Like, what's the pipeline?
Yeah, I think that's a very hard problem to solve for us because we have, I think close to 1,000 teams right now. We're trying to enforce a convention where each metric can have the service name or the team name maybe, and then based on that, we'll be able to link back the metric to the team that owns it, and then we'll be able to add some notifications there.
So just a quick question. Maybe you said that, so sorry if I missed it, but is it an open source project, that's the load balancer?
No, but we're happy to kind of collaborate if there's interest and to make it open source to help kind of maintain it together. We're definitely open to that. Yeah.
Any other question? Yes.
If you know you have a question, please raise your hand earlier so we can, like, during the first question already walk.
Okay. How do you deal with restarts of the StatsD exporter?
So, yeah, when the exporter restarts, we do end up losing some samples, but that's, we think, the same as with any target restarting. Basically, it ends up being treated as a counter reset by Prometheus. And as Pedro kind of mentioned, we've kind of implemented this created timestamp that Bartek talked about yesterday by emitting a 0 sample before the first scrape. So that also gives us a way to calculate the first rate when a time series appears correctly.
And do you sometimes have the case where too many restarts at once and a subset takes too much traffic and so they all bootloop, basically?
Right now we don't, because we do have this load balancing, so resources tend to end up being well distributed. And we can auto-scale, because of the consistent hashing, we can auto-scale and we can add more resources if we detect high memory usage.
Amazing. Maybe last question, anyone?
Okay, thank you, Filip.
Thank you.